So in the previous few classes we have discussed about the surface characteristics, geometrical as well as the physico-chemical characteristics. And when two surfaces, when they come into contact, what happens? The elastic deformation as well as the plastic deformation. Also we have seen when there is a relative motion between the two surfaces, what happens? There is a friction, the frictional force which is acting, and the ill effects of friction, as well as we have seen where the removal of material from both the surfaces which are interacting. Also we have discussed about the third body wear generated from the wear particles. Now we move on to lubricants and lubrication regimes. The lubrication is required in order to avoid the ill effects of friction and wear. The contents of this presentation will include the petroleum breakdown, the lubricants, the lubricant properties, the lubrication regimes, the hydrodynamic lubrication, elasto-hydrodynamic lubrication, boundary lubrication, soil lubrication, and hydrostatic lubrication. So basically these lubrication regimes refer to those lubrication areas wherein depends on the film thickness. So right from a few micron thickness to boundary lubrication, that is of the order of few nanometers, the lubrication regimes varies, which is dependent on a ratio called the lambda ratio, which we will discuss in detail later. Now we move on to the manufacture of lubricants. So basically the lubricants, the mineral oil lubricants is obtained from the petroleum breakdown. So crude is distilled in an atmospheric column to remove light ends like gasoline, kerosene, etc. And then the reduced crude is then distilled under vacuum to get base stocks of different viscosities. So base stocks are actually the essential component of any lubricant. So lubricant consists of base stocks as well as additives. Many times it happens that the base stocks are not able to meet the required functions of a lubricant, hence we have to add various types of additives. So these additives satisfy the requirements, functional requirements of any lubricant. So the base stock is sometimes referred to as lubricating oil or lube. Base stocks are generally petroleum based or sometimes they are synthetic. So nowadays the usage of synthetic base oils are increasing. So petroleum based oils are widely used and mainly considered here. When we do a crude oil breakdown, what we obtain is the high volatile components initially and the gases, petroleum gas, liquefied petroleum gas, the gasoline or the petrol, and then the aviation fuel, the kerosene oil which is used as a fuel, as well as diesel oil, furnace oil, and then heavy fuel oils. Then we obtain the lubricant base stock, and the last one obtained is the asphalt which is used for laying the roads. So petroleum base stocks are a mixture of various hydrocarbons. As we mentioned earlier, the physico-chemical properties of a base oil will not be able to satisfy all the functional requirements as a lubricant, hence many types of additives are added to enhance their properties. So additives are also extensively used to improve the tribological properties, generally to reduce the friction as well as the wear. So base oil should have some essential properties like anti-friction properties, anti-wear properties, anti-corrosion properties, then resistance against sludge formation, resistance against residue formation. There should be sufficient seal compatibility and also additive compatibility. When you add additives, it should be compatible with the chemical nature of the base stocks. Also it should have less forming tendencies and When it is mixed up with water, it should be separating from that. So that is called the demulsifying ability of any lubricant. The base oil has these essential properties, like it should have a high viscosity index. Viscosity index is basically a measure of variation of viscosity with respect to temperature. It should have a high flash point as well as fire point. The total acid number should be low. That means the acidity of the oil should be low. Amount of potassium hydroxide added in order to neutralize the lubricant. So it should be less than 0.05. And the variation of viscosity with respect to temperature should be low, and the evaporation loss as well as the saturate content. Lubricants, as we mentioned earlier, there are mineral oils as well as synthetics, and there are solid lubricants as well, and greases, which are essentially a mixture of the mineral oils as well as the solids. A lubricant is a substance introduced to reduce the friction between moving surfaces. It may also have the function of transporting foreign particles. So a good lubricant possesses the following characteristics. It should have a high boiling point. It should have a low freezing point. This is essential in order to ensure that it functions at low temperatures. It should have a high viscosity index. It should have sufficient thermal stability and should be preventing corrosion as well as resistance to oxidation. The major functions of a lubricant is to reduce the friction, to provide a fluid film which separates the two surfaces, and to lubricate the bearing, to seal voids. And we know that during the interaction between the two surfaces, there will be temperature rise. So if this temperature rise is not contained, or if the heat remains within the system, then it will cause other effects like deformation of the surfaces, chemical reactions which are happening on the surfaces. So in order to prevent all this, the heat has to be removed. So the lubricant acts in order to remove the heat, or it flows away the heat which is generated. Also it should have the function of removing the particles or debris which is formed from wear. So if not removed, these particles will act as third body particles and it will cause further wear and deterioration of the surfaces. Sometimes this will lead to the contamination of the lubricant as well. The properties of lubricants should have, we mentioned earlier that it should have sufficient viscosity and flash point as well as fire point. Vapor pressure, miscibility means it is the ability of the lubricant to mix up with other lubricants. Oxidation stability in order to prevent oxidation and further acid formation. Anti-foaming abilities, and it should have low ash and sulfur content. Foaming happens when it is mixed up with atmospheric air, and it leads to oxidation and related effects. So anti-foam agents are added as additives in order to reduce this foaming tendency. Vapor pressure or equilibrium vapor pressure is the pressure of a vapor in thermodynamic equilibrium, a closed system. So this is also related to the vaporization of the lubricant. Demulsifiability is the ability of a lubricant to separate out from water. This is critical in the case of turbine oils. Viscosity index. So as we mentioned earlier, viscosity index is the oil quality indicator, which is a measure of variation of viscosity with respect to temperature. The viscosity index was developed by Dean and Davis in the year 1921. So they conducted a number of experiments in order to evolve a large amount of data which gives the viscosity values of various lubricants. The pour point of a lubricant is the lowest temperature at which it will pour or flow under prescribed conditions. So the pour point has to be very low, and it ensures that it flows at a lower temperature. There are other parameters like flash point and fire point, which are related to the ignitable mixture which forms with the lubricant. Miscibility is the ability of the lubricant to mix in all proportions, forming a homogeneous solution, and should have sufficient oxidation stability as well. The water content should be low, and water actually forms as a result of the chemical reaction which is happening on the surface, especially in the case of engines. This water content has to be monitored. Similarly, the ash content as well as the sulfur content, which will cause the deterioration of the lubricant over a period of time. We mentioned earlier that viscosity index is a measure of the variation of viscosity with respect to temperature. So for determining the viscosity index of a test oil, the following procedure is adopted. So it is compared with a set of oils from the Gulf Coast oil group as well as Pennsylvania oil group. The test oil is compared with the two different oils, one from the Gulf Coast oil group and another one from the Pennsylvania oil group, in order to determine viscosity index. So the viscosity values of all these three oils at 100 degrees centigrade remains the same, whereas at 38 degrees centigrade it will be different. So these values are available in the following chart, and one can determine the viscosity index of a particular oil comparing these two groups of oils. Lubricants, there are greases as well, which are oils that are thickened with solids like calcium stearate, sodium soaps, etc. And one major advantage is that they do not flow easily and remain within the system. So greases are generally applied where regions that can be only lubricated, not very frequently. So those regions which does not need continuous attention can be lubricated with greases. So the effect of temperature on viscosity. So we know that for liquid lubricants the viscosity reduces with respect to temperature. One relationship is given by this log to the base E eta is equal to A plus B by T, where A and B are constants depending on the properties of the fluid. So these are determined based on a number of experimental data for that particular lubricant. So eta is the viscosity of the fluid. So the effect of pressure on viscosity is very important, because many of the anti-friction bearings, they operate under very high pressures, and the viscosity variation with respect to pressure is a major concern. So the relationship is actually eta equal to eta naught into e to the power of alpha p, where eta naught is absolute viscosity at atmospheric pressure and alpha is the pressure coefficient of viscosity. Again, this pressure coefficient of viscosity is again determined by a number of experiments for that particular lubricant. Each lubricant is specific to a particular application. So we know that a gear oil is different from an engine oil. Also, a lubricant which is used in an anti-friction bearing cannot be used in a full-filling bearing like a journal bearing. So each lubricant is specific to that particular application. So there are rigorous tests which are imposed by various specifications which keep evolving. There are various standards available, and one has to remember that there is always a lack of correlation between laboratory tests and real systems. So many times the correlation problems are worse in the case of tribological tests. Now we move on to lubrication regimes. So there is hydrodynamic lubrication where the film thickness is considerable. When we say considerable, it is of the order of few microns. And there is elasto-hydrodynamic lubrication where there are two effects: the elastic deformation of the surfaces as well as a hydrodynamic effect caused due to the flow of the lubricant. And there is mixed lubrication as well as boundary lubrication. Boundary lubrication is the other extreme where the film thickness is very small and there is no continuous film which is observed on a surface. Hydrodynamic lubrication, the loads are taken entirely by the fluid. In elasto-hydrodynamic lubrication, the loads are taken partially by the fluid and the elastic deformation of the asperities. Whereas in boundary lubrication, the loads are taken predominantly by the asperity contacts protected by thin fluid films, and they are of the order of few nanometers. And a mixed lubrication is one in which there is a transition between boundary lubrication and elasto-hydrodynamic or hydrodynamic lubrication. So there is a schematic of the lubrication regimes where one can see the film thickness is considerable in the case of hydrodynamic lubrication, whereas in the case of boundary lubrication the film thickness is of the order of few nanometers, of the order of few molecular sizes. The variation of friction coefficient for various lubrication regimes, the extreme case is hydrodynamic lubrication, the other extreme is unlubricated surface where the friction coefficient is very high, many times it is more than 1, and one can see in hydrodynamic lubrication it is 1 in 1000. The coefficient of friction is very low. This is actually a variation of the wear rate with respect to the lubrication regimes. So hydrodynamic it is very low, elasto-hydrodynamic again it is very low, whereas in boundary and unlubricated surfaces it is high, and one can see the seizure which occurs because of an unlubricated surface over a period of time. The Stryber curve shows two extreme conditions, the boundary lubrication as well as hydrodynamic lubrication. With respect to the lubrication parameter, the coefficient of friction, the variation of the coefficient of friction with respect to eta V by P. So dry friction, coefficient of friction is very high, whereas in the case of elasto-hydrodynamic lubrication, the friction coefficient is very low, and in the beginning of the hydrodynamic lubrication, which depends on the speed, the journal speed or the relative speed between the two surfaces, it is very low, whereas when the speed increases, the friction coefficient also increases. This is due to the fluid shear effects. In hydrodynamic lubrication, the mechanism is mainly by the relative motion of the two surfaces, so operates due to the hydrodynamic action. So there are two effects, the pressure induced flow as well as the velocity induced flow. There is an unbroken film of oil. Generally the bearings, the hydrodynamic thrust bearings, hydrodynamic journal bearings, tilted bed bearings, relay step bearings, etc., they operate under hydrodynamic lubrication. The ratio of the film thickness to average roughness is quite high in the case of hydrodynamic lubrication. It is more than 5. Whereas in the case of boundary lubrication, the other extreme, it is less than 0.5. We see a typical hydrodynamic lubrication in a journal bearing. So there is a sleeve which is stationary and a journal which is otherwise known as the shaft which rotates. So it's a typical example of a journal bearing. And there are certain applications, like in the case of crank and piston pin bearings, both are under hydrodynamic lubrication. The crankshaft, the big end of the connecting rod will be assembled in the crank, and it is under hydrodynamic lubrication. Now we see the mechanism of the hydrodynamic lubrication. When two parallel surfaces both are stationary, the velocity profile will be like this. The maximum velocity will take place at the mid region, whereas at the extremes, that is close to the surfaces, the velocities will be very low. due to the boundary effects. When one plate is moving relatively with the other plate, the velocity profile will look like this. The upper plate is moving with some velocity, whereas the lower plate is stationary, so the velocity varies in a linear way. The maximum velocity will be close to the velocity of the moving plate. Whereas on non-planar plates, the velocity profile will be like this. So due to the space motion, there will be other effects. So here the cross-sectional area are different at the entry as well as at the exit. Hence there will be a squeeze effect which is created. So this is actually causing the load carrying capacity in a hydrodynamic bearing. So there is a pressure induced flow as well as a velocity induced flow. The velocity induced flow generated by the relative motion between the two surfaces, and due to the squeeze motion there is a pressure induced flow as well. A combined effect will be able to carry a load. The hydrodynamic bearings, it is a combination of the Poisson flow, the pressure induced flow as well as the curved flow, which is the velocity induced flow. So when the journal is at rest, the journal will touch at the bottom of the sleeve. When it starts rotating, due to the friction effects, it will mount onto one side depending on the direction of rotation. So here on the right side, because the journal is rotating in a clockwise direction. The fluid film is also carried along with that, along with the rotating journal, and due to the pressure generated, the journal will shift to the other side and it comes into a dynamic equilibrium state. When a load is applied, the journal will be able to carry the load because of the squeeze effect as well as a relative motion between the two surfaces and the resulting hydrodynamic action. Now let's see what are the geometrical as well as operating parameters of a journal bearing. The major parameter is the fluid film thickness, the diameter or radial clearance, which is a constant once the bearing is designed, the eccentricity, which is the distance between the two centers, the eccentricity ratio, which is the ratio of eccentricity to radial clearance, the load carried, the angular speed, the fluid viscosity, and the attitude angle. Attitude angle is the angle between the line of action of the load and the line joining the center of the journal as well as the bearing. So depending on the speed as well as the load, the attitude angle will vary. So this is the configuration of a journal bearing. The width of the bearing, the radius of the journal, the radial clearance, the eccentricity as well as the rotational speed. This shows the pressure profile in the case of journal bearing. The film thickness is highly enlarged and shown, and the pressure profile is shown where the maximum pressure is very close to the minimum film thickness, and the journal is rotating in a counterclockwise direction here. In hydrodynamic lubrication, the pressure is developed in a convergent fluid film. The pressure is usually less than 5 megapascal, so it is almost 50 times the atmospheric pressure. The film thickness usually exceeds 1 micron. The lubrication, as we mentioned earlier, it is due to the pressure induced as well as the velocity induced flows. And we know that as the clearance increases, decreases the coefficient of friction because of the higher film thickness, but reduces the load carrying capacity. A very thin film is likely to cause the rubbing of high spots on the surface of the journal as well as the sleeve. In hydrodynamic lubrication, perfect lubrication is enhanced by low temperature. If there is a high temperature, it will cause the variation of viscosity, and hence the load carrying capacity will reduce. Hence a low temperature. optimum viscosity, low load, there should be adequate supply of oil, and it should be operating at a high speed and slow acceleration from rest. If the journal is accelerated very fast, it will cause the disruption of the film and a hydrodynamic effect will not be generated. A step bearing is basically a bearing in which there is a change in the cross-sectional area, a uniform cross-sectional area at a particular region, and another region different area of cross-section. So it causes a hydrodynamic effect due to a step. Now we move on to hydrostatic lubrication. The essential features of hydrostatic lubrication: there will be a land as well as a runner, and there will be a recess on the land. The oil flows into the recess region and it flows radially outward, and due to the motion of the oil, which is under high pressure, a load can be supported on the runner portion. The features of a hydrostatic bearing: it has got very high load carrying capacity at low speeds. We know that a general bearing can be operated at high speeds, whereas hydrostatic bearing can be operated at low speeds. It has very low coefficient of friction. There is high positional accuracy in high speed light load applications. Many times wherever there are positional accuracy required, hydrostatic bearings are used. It has got high stiffness and high damping capabilities. The major disadvantage of a hydrostatic bearing is the additional equipment required for its operation. So the hydraulic circuit required for operation of a hydrostatic bearing is an additional feature. So the mechanism of lubrication: the lubricant is pumped at a high pressure to the pocket, as we mentioned earlier, or to the recess portion. Oil flows radially outward through the narrow space between the runner and the land. The pressure acting on the thrust plate lifts the load W. Thrust plate is the runner. So this is hydraulic circuit required for hydrostatic bearing. There will be a tank which stores the lubricant, and it is pumped through a flow control valve. There will be filters in order to remove any debris, and there is a compensating element which actually is required for controlling the pressure in the recess portion. On the land portion as well as the runner portion, the runner, the load is applied, and the lubricant which flows out returns through a flow return line into the tank. The excess pressure is actually released by a pressure relief valve, and which flows the lubricant back to the tank. Now let's see the function of the compensating element. So there are two systems, basically a constant supply pressure system as well as a constant flow rate system. In the constant supply pressure system, there will be a capillary tube or an orifice. Capillary is basically a long tube in the direction of flow, whereas an orifice is a short tube in the direction of flow. So it's a constant flow rate system, there will be constant flow control valves. In the case of capillary, the flow is due to shearing motion, hence it is proportional to the pressure difference or between the inlet and the exit. In the case of orifice, it is due to the inertia effects, hence depends on the density. So flow is proportional to the square root of the pressure difference or the delta P. Now we move on to the analysis of a circular step bearing. So RO is the outer radius, and Ri is the radius of the recess, and H is the film thickness. The flow rate is given by pi h cube PR divided by 6 eta log to the base E RO by Ri, where H is the film thickness, PR is the recess pressure, and eta is absolute viscosity of the lubricant. The load carrying capacity is given by W is equal to pi PR RO squared minus RI squared divided by 2 log 2 base E RO by RI. So when the resist pressure is high, the load carrying capacity will be high. There are hydrostatic journal bearings as well. The working principle is same as that of hydrostatic thrust bearings. The film thickness is not uniform and hence the pressure development mechanism is also slightly complex, and the bearing pressure is considerably altered due to the relative velocity between the journal and the bearing, resulting in shaft rotation. So they basically a tilted bar bearing, a thrust bearing, which is used in the case of propellers in marine vessels. So in order to avoid the vibrations from the propellers to be transmitted to the hull, there will be thrust bearings which essentially dampens the vibrations. So the vibrations will not be transmitted to the hull. Now, when we reduce the film thickness, we go to the elasto-hydrodynamic lubrication design. Lubrication design in which the lambda ratio is small compared to hydrodynamic lubrication design. There are non-conformal surfaces, or the surfaces do not closely match together. There will be the elastic deformation of the lubricated surfaces. There is a conversion in the fluid film. There is a sliding motion or relative motion between the surfaces. This is the presence of a lubricant. Elasto-hydrodynamic lubrication, there are two classifications: the hard ESDL as well as the soft ESDL. So most of the anti-friction bearings, the gear contacts, cam contacts, etc., they operate under hard elasto-hydrodynamic lubrication. There are high loads acting over small areas, high pressures and temperatures. The pressures are of the order of few gigapascals. The minimum film thickness usually exceeds 0.1 micron, but will be much less compared to a full film lubrication. In the case of soft ESDL, there are loads are low, there are elastic deformations, moderate pressures and temperatures. The pressures will be close to 10 times the atmospheric pressure, that is about 1 megapascal. So many of the rubber seals, they operate under soft elasto-hydrodynamic lubrication. Now, when we think of the anti-friction bearings, they carry heavy loads. Now, how these are affected? This is basically because of the high pressures which are acting and which brings in the changes in the viscosity of the lubricant. So we earlier mentioned that the pressure viscosity relationships are important. So given by eta equal to eta naught into e to the power of alpha p, we can see that the viscosity changes exponentially with respect to pressure. So the elastic behavior of the solid under high pressure has to be considered. The viscosity pressure characteristics becomes important, and hence these bearings are able to support very heavy loads. Now why these are important? Because there are billions of bearings in use. The bearing life is related to the lubricant properties and film thickness. The higher the viscosity or the optimum viscosity, with higher pressure it will be able to carry higher loads. A reduced lubricant flow into the inlet zone causes lubricant starvation, and it will lead to the failure of the bearing. Operates when the speeds are high as well as when the loads are high, and sometimes due to temperature changes the viscosity changes, and hence load carrying capacity will reduce and it will finally lead to the failure of the bearing. In the case of boundary lubrication, and the film thickness is still small, there is no continuous film, the lubricant molecules they stand out like the bristles of a toothbrush or in the carpet, and it will separate the surfaces. But at some points there may be asperity level contacts taking place. The sketch shows a boundary lubrication regime. So when the pressure of the contact exceeds beyond DHL conditions, the contacting asperities deform plastically. The number of contacts increases and the fluid film thickness decreases. Essentially, the surface contact becomes a major part of the load supporting system. So the boundary lubrication is enhanced by long chain hydrocarbons. A typical example is stearic acid, which has got about a few microns. The length of the hydrocarbon chain is approximately 1% of the asperity peak heights. So these hydrocarbon chains, they stand out like the bristles in a carpet and hence separate the surfaces. They can oscillate from their positions. The free end can oscillate from their positions, and they perform the function of a lubricant. Sometimes there will be chemical reactions between the lubricant molecules and the material of the surface. It will lead to some boundary films being formed on the surface, and many times these are beneficial, or sometimes they are detrimental in terms of wear. The coefficient of friction will be slightly high in the case of boundary lubrication. We find rubbing surface of piston ring, the crosshead, machine tool guides, watches, clocks, production machinery, door locks, etc. They operate under boundary lubrication regimes. Now the last part is solid lubricants. A solid lubricant is a solid layer separating between the two surfaces. A typical example is a molybdenum disulfide in an epoxy resin baked onto the surface. So solid film may be formed in a chemical reaction, like in the case of aluminum oxide on aluminum surface. So the coefficient of friction is given by Sm by Pm. The friction coefficient is based on the shear strength of the softer surface as well as the hardness of the softer bulk material. If the layer is strong, then it will not be sheared, the parent material will be sheared, and the solid layer prevents the formation of junctions and no junction rope takes place. If the solid surface is soft, then shearing of the solid surface takes place. One major advantage is that they can be operated at low sliding speeds, low load and elevated temperatures. Graphite is a typical example. Molybdenum disulfide applied in various formats is also another example of a solid lubricant. There are polymers as well as polymer composites like polytetrafluoroethylene, ultra high molecular polyethylene, nylon, polyester, etc. Now, how do they function? So they are able to carry heavy loads because they can shear in a lateral plane, whereas a transverse load can be carried. So in the direction of motion, the lamellas easily shear over each other, resulting in a low coefficient of friction. A solid lubricant is useful for conditions where conventional lubricants may not be applied, may not be adequate, and where there is a reciprocating motion, high temperature, there are extremely high contact pressures. A typical graphite structure, a hexagonal structure which can shear in a lateral plane, whereas it can carry transverse loads. And many times water vapor is required in order to increase the graphite lubrication. The absorption of water reduces the bonding energy, hence the lubrication effects are increased. A molybdenum disulfide has a similar structure as that of the graphite. And the hexagonal pressure sucker has an intrinsic property of easy shear, and one major advantage is that it can operate at very high temperatures. This is a typical structure of a layered molybdenum disulfide. Boron nitride as well as PTFE are also solid lubricants. They are widely used.